In this video, we're going to start talking about the derivative. So by the end of this lesson, you should be able to answer the following little question. What is the derivative and why is it useful? And by the end of this unit, which this is the last lesson in this unit, so at the end of this lesson really, you should be able to answer how do we find the slope of a line using only one point. Okay, so let's do the warm-up. Thinking back to lesson 1, let's write one sentence that relates the terms slope, secant line, tangent line, and limit. So we learned in lesson 1 that the limit of the slope of the secant line is the slope of the tangent line. Okay, so just to recap, remember in lesson 1 you did the limit tables and you did that with slopes of secant lines, and then we showed that we could estimate the slope of the tangent line based on those tables. All right, next we have what is the formula for the slope of a line. So that's m is equal to y2 minus y1 over x2 minus x1. Okay, and finally list all the words you know that are equivalent to slope. So that's really been a big theme of this first unit, is all the different ways that we represent slope. So we kind of had two different kinds. So when we have 2 points, we had things like average rate of change, or average velocity. And then we also had some ways that we could find it with 1 point. So that's our instantaneous stuff. So we had instantaneous rate of change, and instantaneous velocity. Okay, so in this lesson, we're going to add to that list by giving you another way to think about slope. And that is the derivative. So the derivative of a function is, well, it has a couple of different definitions. We could view it as the slope of the tangent line to the function, or we could view it as the instantaneous rate of change of the dependent variable with respect to the independent variable. So we usually write this the change in y over the change in x. So change in y over change in x. And just like we did with limits, we have a few different ways of writing derivative in notation, and we kind of choose each one depending on what the situation is. So do we want to focus more on the function, or do we want to focus on what variable that we're taking the derivative with respect to? So depending on how your problem goes, we may want to use different notations. So the first one is this prime notation. So f prime of x means the derivative of the function f. So we're not really focusing on x so much, we're just focusing on the name of the function. We also have d dx of f of x. So here we mean the derivative of the function f with respect to the variable x. So it's kind of similar to the first one, except now we also care about which variable we're taking the derivative with respect to. We also have y prime, and this is probably the notation with the least amount of information, but we'll still use it sometimes. So this is saying the derivative of the variable y. So here we're not even using function notation. We're just assuming that we have like y is equal to some function of x, and we're taking the derivative of whatever variable is in there. And then finally we have dy dx, and that means the derivative of the variable y with respect to the variable x. So this one is kind of similar to the second one. So notice both of those focus on which variable you're taking the derivative with respect to. We'll definitely be using that notation sometimes in later sections. So it's important to know all four of these though. So you shouldn't pick just one. You should make sure to shop around, try out different ones and see which one you like. However, we will see all four as we continue in this class. Okay, now let's talk about how to actually calculate the derivative. So in this section, we're not going to calculate it algebraically so much, but I at least want to show you the formula. So remember in the warm-up, we had that sentence, the limit of the slope of the secant line is the slope of the tangent line. And this is precisely where this limit definition of the derivative comes from. So that's what this is. Limit definition of derivative. So let's kind of take that sentence from the warm-up and see if we can match it to parts of this formula. So f prime of x we know is the derivative of the function f equals always means is. This piece right here looks a lot like the slope formula. So actually what this piece is saying is the slope of the secant line or the average rate of change. And finally, we put a limit on the front because we want to find the slope of the tangent line. So the limit as 2 points get infinitely close together. So that's the reason we make h go to 0 and not like x or something like that. So h is like the distance between 2 points, and if we make that go to 0, what's happening is those 2 points are getting so close together that they kind of look like 1 point. Okay, so why do we choose the notation f prime of x? Well, that's because here we care more about the function name than the variable. Oops. Okay, there we go. More than the variable x. So for now, we're only dealing with one variable functions. So later on, you might start dealing with functions that have more than one variable that you can plug in. So like x, y, and z, for example. And in that case, it would be very important to know which derivative you're taking with respect to what variable. But here, we don't have to care about the fact that x is our variable so much, only because it's the only variable. Okay. Another way to think of this is imagine a super powerful magnifying glass, and as we zoom out on the graph, the points of the secant line appear so close together that they look like 1 point. So that's what this is doing. So here, it looks like we have 2 points, but when we zoom out and zoom out and zoom out, they end up looking super close together, and it's like we only have 1 point. Okay, so let's summarize that. So as we zoom out on the graph, the points of the secant line appear so close together that they look like 1 point. And that's our tangent line. So that's the idea of finding the slope of a line using only 1 point, is that we actually don't have 1 point, we have 2 points that are infinitely close together, if that makes sense. Okay, so first, let's think about the derivative at individual points. So remember, the derivative is a rate of change. And that's an important concept. So rate of change. So for example, let's say the number of E. coli bacteria after T hours on a piece of chicken is N is equal to F of T. What is the meaning of the derivative F prime of 5 and what are its units? Okay, so if F is the number, then F prime must be the rate of change of the number. Okay, so what does that mean? Well, F prime of 5 is the rate of change of the bacteria population at T equals 5 hours. So at the 5-hour mark, we could say. And so in these applied situations, we always want to think about units. So here we've got number of bacteria per hour. So that would be our units. So the units are bacteria per hour. So anytime you're dealing with a derivative, it's always going to have units that are some kind of unit divided by another unit. So a lot of times that'll be time, but not necessarily. Okay, suppose there is an unlimited amount of chicken for the bacteria to feed on. Which do you think is larger, F prime of 5 or F prime of 10, and why? So the answer for this could go both ways. So maybe you're in the camp that, well, if there's unlimited chicken, then the bacteria would just keep eating the chicken, and so they would grow exponentially and get infinitely large of a population. F prime of 10, or sorry, so that's if you think F prime of 10 is bigger. However, what happens if, yes, they have unlimited chicken, but something else happens? So it's not necessarily true that F prime of 10 is bigger than F prime of 5, so I'll let you think about that one and decide which one you agree with more. And if the supply of nutrients is limited, would that affect your conclusion? So that may change your answer from part B, but again, I'll let you think about that one. Okay, so now we'll think about the derivative as a function or at all possible points simultaneously. So for example, we're going to match each of the functions a through d, so the blue graphs, with its derivative 1 through 4, which are the red graphs, and we want to give reasons for our choices. So let's start with a. So a, we're looking at this graph here, and if we look at our derivative graphs, we want to find something that sort of so if we think about the tangent line to A, it starts out as a negative slope, but then it gets more and more positive until finally it turns negative again. So let's look at our graphs on the right and decide which one kind of matches that. So if we look at number 2, we have something that gets larger and larger and larger until a point, and then it gets smaller and smaller and smaller again. So I think number 2 is a good match for A, because the slope of the tangent line increases until x equals 0 and then decreases. So when you're first starting with these, it's definitely a good idea to make sure you're drawing a bunch of tangent line examples along your curve to give yourself an idea of what's happening. Okay, next let's look at B. So that's this graph right here. And B, we notice, has 2 points where, how do we really define a tangent line there? So if we look at this point right here, it's so pointy, can we really say that a tangent line has a particular slope at that point? I don't think so. So let's go and look at our derivative graphs and see if there's something that says we can't define the derivative at those 2 points. And I think number 4 fits the bill because we have these 2 discontinuities. So we'll say number 4 because there are 2 points where the slope of the tangent line is undefined. Okay, next let's look at part C. So that's this graph. And this one you might think is a little easy to match because it has a horizontal asymptote. So we probably need the derivative with a horizontal asymptote. So we probably want to go with 1, but we can also think about the slope of the tangent line. So if we think about these tangent lines going along this graph here, so it switches from negative to positive at x equals 0. And the graph has a horizontal asymptote, but definitely want to think about the tangent lines. Okay, and then finally let's think about part D. So that's this graph. So the only one left is number 3, but we can still reason why that should be the answer. So because the slope of the tangent line decreases, then increases, then decreases again. So let's look at our tangent lines to this and kind of think about it. So here we're decreasing as we get up to that top of that curve, and then we're still, now we're increasing. So we turn 0, and now we're increasing again, increasing, and now we're decreasing again all the way down to the bottom. So yeah, so that makes sense. D makes sense with 3. Okay, so that was a short introduction to matching up graphs with their derivative graphs, and that's not an easy concept, so definitely make sure that you go back through this example and try to work it again yourself. Okay, so on this note, if the derivative of a function exists, we call the function differentiable. Okay, so let's look at that one from part B again. So there are 2 points where the slope of the tangent line is undefined. So that was those pointy points here, and that corresponds to discontinuities in the derivative graph. So this is what we call f, this is f prime. So discontinuities, and we can match these up. We can say that one corresponds to that one corresponds to that one. So this corresponds to discontinuities in the graph of the derivative because the derivative does not exist at these points. Okay, but that's not the only way the derivative may not exist. So let's look at some other graphs of functions and see why the derivative may not exist. So here in this first one, we have kind of the same idea as that pointy curve that we just talked about. So we have what's called a cusp or a corner. So corner was in that part B example. A cusp is what you see here. It looks like a curvy corner. The next one we could have is a jump discontinuity. And that makes sense because remember we just defined a derivative as a limit, and a limit does not exist at a jump discontinuity. So limit does not exist. And then finally we could have a vertical tangent line. So this happens when your curve is so steep that the tangent line is vertical, and the problem with that is the slope does not exist. So remember, when you have a vertical line, you have an undefined slope. So these are kind of the things that can go wrong with your formula. You could have a cusp or a corner, meaning you have multiple or infinite slopes, or you could have the limit not exist, or you could have the slope itself not exist. Okay? Let's see, what do we want to talk about now? Okay, so now we're going to switch topics just a little bit. We're going to see how the derivative can be useful in estimating functions. So first we want to recall, what 2 quantities do we need in order to find the equation of a line? Well, we need the slope of the line and we need a point located on the line. All right, and then I want you to write the slope-intercept form of a line and the point-slope form of a line. So those are y is equal to mx plus b, and y minus y1 is equal to m times x minus x1. And these are going to be useful in our next thing. So here we're talking about lines, we're talking about derivatives. So remember the goal of this lesson, or well, I don't want to say the goal of the whole lesson, but one of the goals of this lesson is to relate secant lines and tangent lines through the derivative. So we know how to find secant lines. You've done that since high school. You find a slope, you might be given a point, and then you just find the equation. Now the tangent line is going to be that line where we only have one point. So the tangent line is just the line where m is equal to the derivative. Okay, so you already know how to find equations of lines. This is just a different way now of finding the slope versus using the slope formula. Furthermore, a tangent line to a curve at x equals a can approximate the function at values of x very close to a. So to kind of see how this works, take a minute, go to Desmos, and graph the following equations. And if you zoom in near the point of tangency, the graphs are going to appear to overlap. And so what I've given you there is a function and its tangent line. So what that tells you is that you can use the line to approximate the function in really, really small intervals around whatever point you're worried about. And so why would we want to do this? Well, it's useful to be able to approximate functions with tangent lines because it requires less computations for a computer than evaluating a complicated function. And this process is called the linear approximation, or the linearization of a function. So again, you can't use a calculator in this class, but we do want you to think about how you might start thinking about approximating things, because honestly, on the job, you're working with computers. That's actually one of the most important things you could learn in this class. So, as an example, let's find the equation of the tangent line to the function f of t is equal to 2.5 t squared plus 6t at t is equal to 2. And I've given you the derivative here because we haven't really talked about how to solve for those yet. We're just going to focus on finding the equation of the line. So, to find the equation of a line, we need a slope and a point on the line. We are given f prime of t is equal to 5t plus 6, which we know is going to be our slope. And we're also given f of t is equal to 2.5 t squared plus 6t. And so this is a way to get a point. And we also know t is equal to 2. So maybe I should say the derivative is a way to get slope. Okay, so first let's find the slope. So all we need to do to find the slope is plug in our value of t into the derivative. So we have f prime of 2 is equal to 5 times 2 plus 6, which is 10 plus 6, which is 16. Second, we find the y-coordinate of a point on the line. So again, we just take our function, plug in 2. So we have 2.5 times 2 squared plus 6 times 2, and that's 2.5 times 4 plus 12, which is 10 plus 12, which is 22. So I have my slope, I have my point on the line, which would be 2 comma 22. So now I can find the equation of a line, no problem. So I'm going to use point slope form, which is y minus y1 is equal to m times x minus x1. And if we plug in what we know that we have y minus 22 is equal to 16 times x minus 2. So if we wanted to turn this into slope-intercept form, because I think we're going to have to graph it on the next page, let's go ahead and distribute the 16. So we have 16x minus 32. And this will give us y is equal to 16x minus 10. Okay, so normally you could just leave it in this point slope form, but since we're going to graph it, it's much easier to graph things in slope-intercept form. Okay, so part B, we're going to use the equation of the tangent line to estimate f of 2.1 and f of 3. So all this means is we take our equation of the tangent line and we plug in the desired x values. So just a reminder, that was y is equal to 16x minus 10, or we could say, really the way we should write this is f of x is approximately 16x minus 10. So we can say f of 2.1, I'll work it over here. So f of 2.1 is approximately 16 times 2.1 minus 10, which gives us 33.6 minus 10, which gives us 23.6. And then if I want to do f of 3, I'd say f of 3 is approximately 16 times 3 minus 10. So we have 48 minus 10, which is 38. Okay, so now let's sketch a graph of f and f prime. So f, remember, was y is equal to 2.5 t squared plus 6t. So this is going to be a parabola. We can get our x-intercepts really quick by setting this equal to 0 and factoring. So we get t times 2.5t plus 6. So this gives us t is equal to 0 and negative 2.4. So our parabola looks something like this. We have a point at 0, and we have a point at 2.4, and I think we can make the scale on the y-axis 3. So we have like minus 3, minus 6, minus 9. And so the parabola looks something like this. And then our tangent line, if we have 1 and 2, and then 3, 6, 9, we have our y-intercept at negative 10, and then we go up 16 over 1, so that puts us at 6, 1. So here we're not going to quite see the point of tangency because it's not a big enough graph, and that's kind of my fault. But we can get an idea of whether the estimates we found in B are going to be an over or an underestimate. So notice here, this is F, this is F prime. The, or sorry, not F prime, tangent line. Okay, notice the tangent line is below the function f. So what that tells me is that the estimates that I found in part B were actually lower than the real function value. So that's what I'm going to write in part D. So f of 2.1 approximately 23.6 is an underestimate. And so is f of 3 approximately 38. So next we want to find exactly how far off these estimates were, and we can do that by finding the relative error. So if you haven't done that before, basically what you're doing is finding how far you are from the actual value as a proportion of the actual value. And so your answer will be written as a percent, and that'll allow you to judge if you have a good error bound or not. So let's do that. So f of 2.1 actually equals 23.625. And f of 3 actually equals 40.5. So if we calculate relative error, we're going to do the estimate minus the actual over the actual times 100%. And this gives us approximately, so here I'm okay if you put this into a calculator, but that gives us approximately 1.05% error. On the other hand, if we do f of 3, we get that error is equal to 38 minus 40.5 over 40.5 times 100%, which approximately gives us 6.17% error. So the thing to take away from this, the reason that I had you do 2 of these is because we want to notice that the tangent line is only good at values that are really, really close to the value of t that we found, that we actually constructed the tangent line with. So remember, for us, t was equal to 2. So well, let's actually put this answer in part E. So t was equal to 2. So the estimate for 2.1 is better than the estimate at 3. And that's because 3 is farther than 2 than 2.1 is. Okay? So estimation can be kind of tricky, but that's really what's super important. So especially those of you who are engineers, you're going to see error bounds a lot in your engineering problems. Because a lot of times there, you don't care as much about the exact answer. You care about whether or not you're in an acceptable bound so the bridge doesn't fall down, or the building, or whatever else you might be creating there. Okay, well, that's the end of lesson 6. Make sure you do the check your understanding, just to make sure that you understand exactly what the derivative is and why is it useful. But that's the end of this lecture.